Welcome everyone to the first keynote talk of WINE 2020, which will be delivered by Professor Yiling Chen. It is my great honor to give a brief introduction of Professor Chen. She is a Golden Micron Professor of Computer Science at Harvard University. She received her PhD in Information Sciences and Technology from Pennsylvania State University. Prior to working at Harvard, she spent 2 years at Yahoo Research in New York University. Her research focused on topics in the interaction of computer science, economics, and other social sciences. Professor Chen was a recipient of NSF Career Award and the Penn State Alumni Association Earlier Career Award. Also, Professor Chen was selected by IEEE Intelligence System as one of AI's 10 to watch in 2011. Her work received Best Paper awards at top conferences such as EC AMAS, SMFest, etc. Professor Chen has co-chaired a number of well-known conferences, including WINE 2013 and EC 2016. So let us look at what Professor Chen will bring us on challenge of incorporating algorithms in decision making. Please join me in warmly welcome Professor Chen to give her keynote talk. Welcome, Professor Chen.
Thanks. Thank you so much for having me. So today I'm going to talk about challenges of incorporating algorithms into decision making. I'll touch on aspects related to fairness, social welfare, and also the disparity arises from the interaction with algorithms. So when we talk about decision making, we usually think about humans are decision makers because of our intelligence. But because of algorithms are not having equal footage in the decision-making process. In fact, humans are the final decision makers, with algorithms providing useful information to facilitate the human decision-making process. So we coin up the term algorithm in the loop, human decision-making, to emphasize that the relationship between algorithm and human in the decision-making process. And a natural question to ask is how algorithm facilitated decision-making actually affects human judgments and decisions, because now we have access to information provided by the algorithm. Is that going to fundamentally change human decision-making process in some ways? So today I'm going to touch on both questions. So the first part of my talk, I'll talk about a theoretical piece of work that's trying to get some insight for the question, how does fairness consideration in algorithms relate to the notion of welfare in economics? So this is based on joint work with Lili Hu. And then I'm going to talk about 2 experiments that we have conducted on algorithm in the loop decision making. So these are human subject experiments. So the experiments allow us to partially answer the question how algorithm facilitated decision making affects human judgments and decisions. So this part is based on joint work with Ben Green. So let me dive into the first part and talk about fair classification and social welfare. So we're all familiar with classification algorithms. So the most standard way of looking at classification is it is an empirical loss minimization problem. So usually we have some loss function and we're giving some training data, so which are labeled data points. And then we want to find a hypothesis function, so which is a classifier from a hypothesis class that classifies the data points such that we can minimize the loss, the cumulative loss. So in this example, we have the squares and the circles, and we're trying to find a linear classifier to separate these 2 classes. And a very commonly used linear classifier is the soft margin SVM. So I'm talking about the linear version. So in soft margin SVM, we hope to find a margin that as large as possible, such that we can perfectly separate the two classes. But often the data that we're having are not perfectly separable. So we're allowing us to incur some, to make some errors. So essentially here is the slack of this data point to its margin boundary. So which is this data point's say in the objective function. So we're minimizing the original objective function, which is equivalent to maximizing the margin, and adding the slack term. Essentially, we're tolerating some level of errors. So this is just the standard soft margin SVM. But when we're thinking about that, our data point are coming from some subpopulations. They have their group identities. So for example, men and women. So I'm having blue and red here. So for the two groups, we're hoping that two groups are being treated equally, so in some fair fashion. There has been a lot of definitions related to what is considered fair. I'm not going to discuss the specific definitions here, but one family of the fairness notions related to treating the two groups equally in some sense. So as a way of doing fair classification, one way of introducing the fairness consideration is to introduce a fairness constraint. So I'm giving a very generic fairness constraint here. And the idea is that if we're thinking about Zi as the group identity, so we have two groups, Zi equal to 0 and Zi equal to 1, and these are the group-related events, then roughly speaking, the fairness constraint is saying that we hope to treat the two groups roughly the same. So we can have a little bit tolerance for our fairness. So epsilon small being that we're treating the two groups roughly equally, having a large epsilon means that the two groups has disparity. So such a fairness constraint captures most of the parity-based notions. So for example, if we want the two groups to have very similar false positive rates. So a natural question to ask is, we actually are going to use classification for something. So for example, if we're going to use the classification algorithm to decide how to allocate limited resources, taking the financial lending application as an example, the classification outcome are going to determine who gets a loan. So that directly affects an individual's utility. So now we're thinking about an individual I who has an attribute xi, his utility is being affected by the classification outcome. So if we're trying to think about classification as a resource allocation tool, then the question to ask is, what happens to individuals' welfare when we add fairness constraints to classification systems? Because ultimately we care about the outcome. So this is a shift to thinking about fairness in terms of a more equitable distribution of benefits to individuals. Before I proceed to talk about what we did here, I just want to briefly mention that there are other researchers who have been promoting that we should consider fairness together with welfare. So for example, Zafra has been introducing notions of fairness that's related to envy-freeness in social choice. And Hidara et al. 2018 and 2019 paper has been thinking about how to introduce a welfare-based fairness notion as a fairness constraint. And the more recent work by Casey and Ababi also considers the impact of the influence of using a machine learning algorithm on the welfare of the individuals. So what we're going to do is we want to understand how do fairness constraints impact the optimal solutions? because the classification outcome are going to affect the utilities of the individuals and also going to affect the utility of the groups. So we took a particular fairness constraint as an example. So this is just a fairness constraint introduced by Zafar et al. In 2017. And the reason we took it is because of the optimization problem is convex. So it allows the analysis to be, it gives us more tools to do our analysis. So what we want to do is we want to ask, how does varying the fairness tolerance parameter epsilon here affect the individual utility and group welfare? Because we know that when epsilon is small, essentially we're requiring fairer outcomes according to the machine learning formulation. But how does it actually affect the individual utility and also the group welfare? Before we can talk about utility and welfare, we have to define the utility functions. So for this particular analysis, we'll assume that everyone prefers a positive outcome. So if we're thinking about the loan application, so everyone prefers to obtain a loan. So that means that when someone gets a loan, the person has utility 1, and when the person is rejected by a bank for his loan application, the person's utility is 0. So the group welfare in this case is just the average utility of the individuals in a group. Okay, so how can we do that? So our approach is to work with the dual problem of the epsilon fair soft margin SVM, because this is the optimization problem. This is a constraint optimization problem. Our objective is to minimize this expression, and then we have a bunch of the constraints. So for each data point, we essentially have a violation of the margin constraint. So this is for each data point I, and then we have a fairness constraint that tells us like how strictly we want to equalize the two groups outcome. So if we look at the dual problem of this optimization, so we know that every constraint associates with a dual variables. So the dual variables associate with each data point. Here we call it mu I. And then we have the dual variables associated with our fairness constraints. And because it's an absolute value constraint, so we actually introduce 2 dual variables, gamma 1 and gamma 2. And the dual variables has a lot of like information. The insight tells us the classification outcome. So the mu I tells us how xi is classified. And the gamma 1 and gamma 2 naturally tells us whether the fairness constraint is binding. And the standard sensitivity analysis will just allow us to analyze if we're changing the epsilon slightly, how that's going to affect the objective function value. So that's the accuracy of the learning algorithm, and that the machine learning, so the principal or the learner cares about. But here, what we're trying to achieve is that we really want to understand if we're changing the value of epsilon, how that's going to change the classification outcome. And that's going to affect the utility of the individuals and also the welfare of the groups. So standard sensitivity analysis won't help us here. But fortunately, the dual variable mu I tells us how xi is classified. So in particular, when mu I equal to 0, it tells us that xi, so the data point xi, is correctly classified. And when mu I equal to c, xi is incorrectly classified. And c is just like a fixed upper bound, and we usually set it to 1 in our experiments. When mu I strictly between 0 and c, it tells us that the data point xi is in the margin. So it suggests a way for us to track the SVM solution path as we're changing the values of our fairness tolerance parameter epsilon. So basically what we try to do is we want to trace mu I as a function of epsilon. And this allows us to track group welfare as a function of mu I. And I want to comment on the computation of this solution path tracing. So it turns out that we can show this mu I as a function of epsilon passes, it's piecewise linear for each individual I. So that means we can fully characterize the welfare impacts in terms of the stable regions. So we just need to keep track of how the points are moving from one partition to another partition. And the algorithmic implementation of this full fairness to welfare passes tracing has the complexity on the same order as solving the standard SVM problem. So essentially, computationally, it's very efficient. So what did we find? So we find that preferring fire solutions, so which means that having lower epsilon, does not necessarily benefit the welfare of the individuals. So it actually can violate the Pareto principle. So the Pareto principle usually says that a social planner should always prefer a feasible allocation that makes everyone weakly better off. So because that's like, everyone is better off, so that's a preferable option. Violating such Pareto principle just means that as we're lowering the epsilon, it's actually possible that algorithmically fairer solution can make everyone worse off welfare-wise. So this subjects to the epsilon fair classification to the leveling down objection in philosophy, because essentially we achieve equity by bringing the welfare of all groups down. So that's like concerning to a certain degree. So we did some experiments of the SVM solution tracing on the adult data set. So this is a data set trying to predict whether an individual's income is higher than 50K or not. So what we're showing at the bottom is the welfare changes. It's the relative welfare changes as a function of the fairness tolerance parameter epsilon. So this is relevant to the unconstrained welfare. So as we can see that the x-axis are the epsilon parameter, so smaller means fairer, and as it grows larger, about around 0.175, the problem becomes unconstrained optimization. So meaning that the welfare constraint essentially goes away. And that's the welfare that we have for the female group and the male group. We normalize that to be the 100%. And then for both groups, we look at as we're decreasing the value of epsilon, whether that group's welfare increases relative to its unconstrained welfare. So as expected, as we're decreasing epsilon, we can say that overall, the female group's welfare increases as we have smaller epsilon, and the male group's welfare decreases as we have smaller epsilon. So this is to be expected in general. But what's interesting is that this is not monotonic. So we highlighted here and also here the non-monotonic part of this solution welfare change path. As we can say that just around here, as we're decreasing epsilon, so we're making the classification more so fair, the welfare for both groups are actually decreasing. So we have decreasing of the welfare for both the female and the male. And similarly, this is another region. If we look at here, both groups' welfare are decreasing. And the top of the figure is just the individual's dual variable mu I. So we're giving some examples of how that changes as we're changing the fairness tolerance parameter. as you can see that there's no clear pattern of the changes, so the individual's solution path can change drastically. Okay. So that's the first thing I want to talk about, is about connecting fairness with social welfare and thinking about how requiring algorithms to be more fair, so more equitable, actually affects the individual's utility and redistribution of resources among groups of people. So what I want to talk about next is moving to the setup of thinking that, oh, maybe algorithms cannot be the sole decision maker in a long time. So we can't really expect algorithms to be the sole decision maker in many social domains. It may just not be appropriate because we have many other considerations and factors to consider. So in such a context, we're asking the question of, if we're thinking about algorithms, it's just providing some assistance to human decision making. So such algorithm in the loop decision making, how does this going to affect the human judgments and decisions? So Ben and I have run a sequence of human subject experiments on Amazon Mechanical Turk, try to understand how human decision judgments are being affected when we're providing some algorithmic assistance. So what I'm going to talk about is, I'm going to talk about two experiments in the sequence that we have conducted. And for both experiments, we considered two settings. So the first setting is a pretrial detention setting. So the pretrial detention is once the individual is arrested, the judge needs to make a decision to whether release the individual for the period that the individual is waiting for trial, or retain the individual in jail. So if the individual is released, then there is the risk that the individual may be rearrested during the period of waiting for his trial, his or her trial, or the individual may not appear in trial. So the judge's pretrial detention decision should consider the risk of not appearing in trial and also the risk of being rearrested before trial. So that's the pretrial detention setting. And the financial lending setting is the home improvement loan application. So this is just an individual applying for a loan to do home improvement. So we consider these two settings. And basically, we first develop an algorithmic risk assessments such that we can give an algorithmic assessment of the individuals in both settings, and then we run our experiments. So in this talk, I'm going to focus in talking about the pretrial detention for most of the time, but I'm going to touch on financial lending results a little bit, but our results in the two settings are qualitatively very similar. Okay, so I want to dive down a little bit and ask some more specific questions. So the first question is about accuracy, because if algorithms are going to give us very accurate predictions of the risk, does that help people make more accurate predictions of the risk than they could if working alone? So does algorithm actually improves people's prediction of the risk? So that's the question of accuracy. And the second question is, again, related to fairness. So do people interact with the algorithm in ways that are unbiased with regard to race, gender, and some other sensitive attributes? So does the interaction actually create any disparity? And the third question is about the decision-making process. So because our general view of having an algorithm to help us making decisions is that algorithms are providing better information to us, and better information can only help us to make better decisions. It's kind of like a general, very intuitive view of thinking about how algorithms can help human making decisions. But is that true? So does the algorithm change people's decision-making process or not? So these are some specific things that we want to look at our experimental data and try to get some initial answers for. So let me start by describe our algorithmic risk assessment and the data for the pretrial detention. So I'm only going to talk about this for the pretrial detention, but the algorithm is very similar for the financial lending session. And I also want to emphasize that our goal is not to develop an optimal algorithmic risk assessment because we're starting the interaction between algorithm and human. So we want to start with a reasonable algorithm for our experiments. So basically we obtained a data set, a large data set from DOJ for the pretrial detention scenario. And then for this data set, because we want to evaluate our experimental subjects' performance, so we selected only the cases where the judges have made a release decision. Because for those cases, we actually know that after the judge released the defendants, whether the defendant failed to appear in trial or was rearrested before trial. So we know the ground truth for those cases. So, and also we only consider cases where the race is either black or white, only these two ethnic groups. So we trained on, so this leaves us about 47,000 defendant cases. So we trained a boosted decision tree on these cases. And the average AUC of our algorithm is about 0.66. So this is comparable to risk assessments algorithms that's being used in practice. And our algorithm are also calibrated across races. And for our experiments, we selected 300 cases from the testing set for our experiments. So let me start by talk about our first experiment. So our first experiment, we want to understand when human is assisted by the risk assessment algorithm compared with human is making decision alone, how that's going to affect the individual's risk prediction. So this is about human judgment, so we're focusing on the risk predictions here. So we have 6 treatments in our experiments. So the first treatment is no risk assessment. So essentially, we only show the participants of our experiments this defendant profile. And I want to comment that this defendant profile has race, so has and gender information. So for example, this is like black male, but the risk assessment algorithm didn't use this information, didn't use any sensitive attributes. So that's the baseline, no risk assessment, just a human decision. And then the second treatment is risk assessment. So in this treatment, in addition to showing the participants the defendant profile, we're also showing that what the risk assessment score for the individual is. So we're essentially showing this sentence to the participants. And in all our treatment, we're asking participants to make a prediction of the risk for the case. Okay. So in addition to the baseline and the risk assessment treatment, we also have 4 variants of the risk assessment, because one natural thing to think about is how we're presenting the algorithms to the participants will affect their assessment of risk, so affect their decisions. So we have 4 variants of the risk assessments. The first variant is what we call the update. So in this variant, we show the participants the defendant profile first, and we ask them to make a prediction. And then after they have already made a prediction, we show them the risk assessment score, and then offer them the opportunity to update their predictions. That's why we call it an update. And then the second treatment is what we call the default treatment. So the default treatment is actually the interface that I'm showing here. That is because the risk assessment score gave a 40% risk, when participants are asked to make a prediction, the default option is already highlighted as 40%. But the participants can freely predict any other value. So this is just, we're doing some priming of the participants to say whether that might affect their judgments. And then the third variant of the risk assessment treatment is what we call the explanation. So explanation is that, so when just showing the risk assessment number, just 40%, participants may not know what factors have already been taken into consideration by the algorithm. So in the explanation treatment, in addition to showing the score itself, we also show what factors contributes to the algorithm believe the defendants having a higher risk or a lower risk. So we give some information about what the factors that the algorithm have already taken into consideration. And then the last variant of the risk assessment treatment is what we call the feedback treatment. So in this feedback treatment, because each participant of the experiments are asked to make predictions for 40 cases, after each case, we tell them the ground truth for that case, such that they can get a sense of how accurate the algorithm's predictions are and how accurate their own predictions are. So these are the 6 conditions that we considered in the experiments. And let me move to talk about some of the findings. So the first question we look at is the prediction accuracy. So this is the prediction accuracy for the pretrial detention. I'm not plotting all the conditions that we had. So I'm just plotting like 3 conditions plus the algorithm alone. So the leftmost one is the human alone one. So no risk assessment. So this is a human decision. The rightmost one is the risk assessment alone. So this is just the algorithm's prediction. And the 2 columns in the middle, so this is the risk assessment. So just showing the risk assessment score, and this is our update treatment. And what we're showing is that we're evaluating the prediction accuracy by Breyer score, so which is just the negation of the quadratic laws. Breyer score of 1 means perfect predictions. So every time makes the correct prediction. And a Breyer score of 0 means completely wrong predictions. So higher is better or more accurate in this figure. And as we can say that no risk assessment has the lowest Breyer score, and the algorithm alone has the highest Breyer score. And with risk assessment, these 2 treatments have better Breyer score than the human alone baseline treatment. And all the differences here are statistically significant. So what it shows is our risk assessment treatment makes people make more accurate predictions. So they're indeed making more accurate predictions, but they can't make more accurate predictions than the algorithms. So they're not really efficiently making use of the algorithms in a way such that can make even better predictions than the algorithms. So the algorithm still makes the most accurate prediction. And we're just taking a look at other treatment and also for both the pretrial detention setting and the financial loan setting. So here is the relative accuracy gain. So we normalize the baseline to be 0, and the risk assessment alone, which is the algorithm alone, to be 1, because it is still giving the most accurate predictions among all the conditions that we consider. So we can say that the update version seems to be performing the best. So the x-axis shows the pretrial retention setting, and the y-axis is the financial lending setting. So the update treatment seems to have the best accuracy performance for both settings, and the feedback setting seems to have the worst. And RA alone, so just showing the risk assessment score, seems to be somewhere in the middle. and the ranking of all the treatment is rather consistent across the two settings. So that's about the accuracy. And the second question that we're curious about is when human is assisted by an algorithm risk assessment, are their decisions unbiased? So in the sense of, is there any disparity arise due to the interaction? And interestingly, we actually find that disparity does arise through the interaction. So this is why we call it disparate interaction. And let me try to explain the figures that we're showing here. So the left-hand figure is showing what we call the risk assessment influence disparity. So we consider the risk assessment influence as, because when the risk assessment assess a case to be a higher risk than the human alone assessment, so our baseline experiments. So we basically look at how much the participants having access to the risk assessment scale increases their risk prediction beyond the risk assessment number, so beyond the algorithm's risk assessment. So what we find is that the increase for the Black defendants is larger than the increase for the white defendants. And the relative is also large. So the disparity that were plotted here on the left is the difference between the risk assessment influence for Black people minus the risk assessment influence for white defendants. So as we can say that the value for the just risk assessment is positive, and it's actually pretty large as a percentage. For update, it's relatively smaller, but it's still positive. And we also noticed that when our experimental participants look at the risk assessment scale and they try to deviate from it to a certain degree, the deviation tends to be negative for white defendants, meaning that they're lowering their risk, but positive for the Black defendants. So that's what we call the deviation disparity, is the deviation for Black defendants minus the deviation for white defendants. So it's also positive for our treatments. For just the risk assessment one, it has a value of 2.3, and for the update one, it's positive, but much smaller. And when we look at all our treatment, so this is just for the pretrial detention setting, the x-axis plus the risk assessment influence disparity, and the y-axis plus the deviation disparity. As we can say that the update treatment seems to be has the least disparity among all the treatments that we're having. So all the treatment where participants have access to risk assessment, and the feedback and the risk assessment predictions are among the worstest. And you can see that the trend are consistent for the two metrics here. So this is somewhat surprising to us because this really means that because of the interaction with the algorithm, participants' prediction of risk or assessments of risk are affected in a way that's different for white defendants and Black defendants. So there's disparity arises due to the interaction. Okay. So we continue with our third question because we're thinking about risk assessment affects the assessment of the risk, so affects the perceived risk. Does it actually affect the decision? So instead of asking participants to make a prediction on the risk, so in our second experiments, we ask participants to make a decision. So basically we ask the participants to decide whether to release the defendant or detain the defendant. So that's what we want to do. And in this experiments, we only compare risk assessment, just the number, that particular treatment, with human alone, so our baseline. And the question that we're curious about is that since we know that risk assessment changes the perceived risk, and if we have better, more accurate perceived risk, and if that's just an input to our decision-making function, we would expect that we can make better decisions. But does it change the decision-making function itself? So in other words, we're curious about is if given a certain level of perceived risk, is the probability of making a certain decision being affected or not? So here we're really thinking about, we don't know what the complicated decision-making function that a decision maker has, but if really the perceived risk is just an independent input, we should expect this probability to be unchanged. And if this is changed, it's evidence showing that, actually just having access to the algorithm risk assessment may change the individual, how individual making their decisions. So in order to answer this question, so we design our experimental condition as follows. So we randomly assign our participants to a control group that is not showing a risk assessment at all, and the treatment group, which is showing the risk assessment score. And because we also want to assess the perceived risk for each group, we again separating them into groups where we ask them to make decisions. So for these two groups of people, we just ask them to make decisions. And for the groups of people here, we're asking them to make predictions. So this will give us the perceived risk. And then we look at whether the decision-making function is being affected. So essentially, we're looking at the probability of a certain decision conditioned on a certain level of perceived risk. So here is what we're saying here. So let me try to explain these two figures. So the left figure is for the pretrial detention, and the right figure is for the financial loan setting. And what we're plotting here is the x-axis are perceived risk for both figures. So this perceived risk are obtained from participants who are only making predictions. This allows us to get the perceived risk. And then the y-axis are the detention rate for the pretrial setting. So this is essentially the rate of a certain decision. And for the loan setting, it's a loan rejection rate. So the value of the y-axis are coming from the groups who are only asked to make decisions. So this gives us the decisions. And what we're plotting is the blue line is we're not showing the risk assessment. So this is our baseline, the human decision only. And the yellow line is when we're showing the risk assessments. And if we expect that the probability of making a certain decision conditional on the perceived risk to remains to be the same across our baseline and the treatment group, then we would expect that the blue line and the yellow line to be exactly the same. And as you can see that for both settings, they're different, so they're not the same. So for the pretrial detention setting, when the perceived risk is higher, the decision maker tends to more reluctant to release a defendant. So the detention rate is higher. And when the perceived risk is lower, the decision maker tends to release more often. So the detention rate is lower compared with our baseline. And for the financial, participants have access to risk assessment. The presence of the algorithmic risk assessment made the decision maker emphasizing more on risk in making their decision. So in some sense, it's not only just to change the perceived risk, it also changes the decision-making process. Let me try to conclude what I have talked about. So I talked about putting the fairness considerations in machine learning in a welfare analysis framework, and think about how fairness in machine learning actually affects the welfare outcome of those people who are subjected to the decisions that the algorithm made. And it turns out that fairness constraints may oppose to the Pareto principle. So this suggests there are more holistic considerations of fairness in the broader context. And the second perspective I talk about is not only look at the properties of the algorithm, but also think about the interaction between algorithm and decision makers. So we show that algorithm in the loop decision making leads to disparate interactions and affects decision making. So one caveat is that we're using lay people, we're using Mechanical Turk workers to run our experiments. So this is really just some evidence of showing that it may affect human decision making. So professionals who go through years of training, they may be more robust in their decision making process when they're interacting with algorithm. But it at least worth studying. And in fact, there is a very new paper that's just come out a few days ago that conducted the first few experiments with judges for pretrial detention to look at how algorithm risk assessment actually affect their decision. So it shows a certain level of changes to the judges' judgment and decisions too. And the overall message that I want to highlight here is we need to expand our analysis of algorithm decision-making or algorithm-assisted decision-making beyond evaluate the models themselves. So we need to put it in the broader context of its application and consider its outcomes and also consider its interaction with human participants. That's all I want to say. Thank you very much.